Like me, I suspect you have heard of Barnard's star sometime in the past, but I did not really recognize its significance until the research I did for this short video. Barnard's star is located within the constellation of Ophiuchus and close to the Summer Beehive Cluster. It is on the edge of the Milky Way rift, observed in the Northern Hemisphere, but is not visible to the naked eye. It was discovered, of course, by Edward Emerson Barnard, who was born in Nashville, Tennessee in 1857 and lived until 1923. Barnard never finished a college degree, but later received an honorary degree from Vanderbilt University, where he previously studied. He was a staff astronomer at two of the most cutting-edge observatories of his time, the Lick Observatory in California and Yerkes in Wisconsin. He discovered many comets and has more than 7 other astronomical objects, not including Barnard's star, named after him. Barnard's star is significant for the tremendous amount of analysis and astrometry techniques he developed to characterize it during an era of pre-digital technologies, of course. This was possible because Barnard's star is the closest star to Earth that is visible from the Northern Hemisphere. Barnard also studied and compiled a catalog system of dark nebulae that bears his name, with 182 objects cataloged by him by 1919. And of course, he has been the recipient of numerous astronomical and scientific awards. Edward Barnard is considered to be one of the most prolific and influential observational astronomers in the history of astronomical science. Now, for no reason other than pure curiosity and bragging rights, I turned my telescope to Barnard's star late one night back in March earlier this year. The starry photos I took were 120-second exposures, and I collected and stacked 10 of them for 20 minutes of integration time. As usual, I cropped and oriented and compared my image to the simulation sky map in Stellarium to confirm the target. Barnard's star was clearly evident in my photograph. It even exhibited a slightly orange tint in color. Here is the full image again, which was taken with a UV IR cut filter to focus on the visible light. But I also imaged the same field of view when using an IR pass filter, which only allows infrared light to reach the camera sensor. From this comparison, it is clear that Barnard's star emits far more infrared light than light in the visible spectrum. The IR pass filter only allows light with a wavelength of 685 nanometers or greater to pass through and onto the camera sensor. All visible light is blocked with this filter. The reason for this apparent differential brightness phenomena is because Barnard's star is a spectral class M star, more commonly called a Red Dwarf star. Stars like our Sun emit most of their light in the visible wavelengths, but Red Dwarf stars have their blackbody radiation profile shifted to the weaker, longer wavelengths. I use the ASI 533 MC Pro color camera to capture these star images. Here, I overlaid the IMX 533 camera sensor quantum efficiency profile on top of an emblematic starlight emission profile. As you can see, above 700 nanometers in the infrared, the sensor does indeed detect infrared light, regardless of the Bayer matrix pixel colors, all the way up to and beyond the 1 micron wavelength. Compared to the visible spectrum, the sensor's infrared efficiency is slightly lower, but even then, the captured signal seems to greatly exceed the visible light. Barnard's star is an M-class dwarf star which burns fuel so conservatively that these stars are very cool, relatively speaking, and can last trillions of years, which is a very long time since the universe is currently believed to be only about 13 to 14 billion years old. Red dwarf stars are the most prevalent stars in the Milky Way galaxy, possibly making up to 70% of the total star population. Barnard star is only 5.96 light-years away from Earth and is much smaller and dimmer than our Sun. In fact, its luminosity is only 1 divided by 2,600 that of the Sun. Hence, its brightness is a dim apparent magnitude of 9.5, even though it is the second closest star system to the Earth. The first being Alpha Centauri system, of course, which is visible in the Southern Hemisphere. Edward Barnard closely studied the star's movement and noted that its angular drift, called proper motion, is 10.39 arcseconds per year, which, not surprisingly, is the largest value of any star due to its close proximity to us. For these and many other reasons, Barnard's star has been a curiosity and important discovery in astronomy. It has been extensively studied and continues to be even now because it is believed to harbor a multiplanetary system. Who knows, it might be one of the first star systems we humans will explore someday in the distant future. So, I photographed it. For fun. Why not? Barnard's star is definitely not an astrophotographer's dream target, but it is a consequential celestial object, and perhaps you and I now know a little bit more about the sky above us and the history of our chosen hobby. Here in Yokohama, gazing at the stars, I am JP Astro Guy. My name is Paul Cheesegel, and thank you for watching another episode of Astrophotography Japan.